Good morning, Doctor. This is Kabanda Arthur from Group SWMA26, and I'm presenting about our project called BABESIOSIS disease detection. Here's the content of the presentation that I'll be basically talking about. The introduction, related work, problem statement, the questions and objectives, and then the contributions and the rest. So I'll start with the background and the introduction. I'll start with the background. Traditionally, parasite detection has relied on heuristic image processing techniques such as the pixel differencing and morphological thresholding. These methods are relatively simple and computationally inexpensive, making them attractive for early automated diagnostic systems. However, despite of them being cheap and fast, these approaches suffer from very high false positive rates. In many cases, the system incorrectly identifies the non-parasitic key structures such as the parasites, which reduces the diagnostic reliability. The major limitations the major limitation becomes more visible when dealing with unconstrained clinical blood smear images. In real clinical environment, blood smears often vary in staining quality, lightening conditions, and cell overlap, making accurate detection much more difficult. And as a result, the system tends to perform poorly, which can delay proper diagnosis treatment, and the consequences may include the several health and economical impact, such as anemia, uh, the Plasmodium species, when viewed under the microscope, because of their similar visual appearance of the ring shape, the similarity increases the chances of the misdiagnosis and incorrect treatment decisions. And therefore, there is a need for more accurate and intelligent detection approaches capable of handling the complex clinical blood smears with a high precision and low false positive rates. That's our introduction. Then that's our background. Then our detection, we shall be dealing with the manual microscopic diagnosis of the game sustained smear images that are subjectively and error prone and also slow. Particularly, we are basically looking at babesiosis, one of the most threatening tick-borne diseases that result in two heavy losses in cattle. Babesiosis is just a parasite. It's a parasite disease in animals that requires timely and accurate detection for effective treatment. We shall basically use the deep learning, which enables the automated medical diagnosis, and we shall use the CNN approach, or the convolutional neural networks, which helps us detect the parasites in the blood smear images. One of our goals is to attain a faster, accurate, and scalable image diagnosis. Some of the recent trends that we have, deep learning, particularly the convolutional neural networks, has significantly transformed the field of medical imaging by enabling faster, more accurate, and more reliable diagnosis compared to traditional image processing methods. Also, CNN is capable of automatically learning important features from the images, and thus reducing the need of manual feature extraction. Another important achievement is transfer learning. This technique allows the models that are previously trained on large datasets to be adapted to medical imaging tasks with relatively small amounts of labeled data. This is especially useful in veterinary and medical applications where collecting and labeling the large datasets can be difficult and expensive. So we have our AI-assisted systems that are now able to detect parasites directly from the game's blood images with the promising accuracy, and the system helps us to reduce the human error, improve the diagnostic speed, and also support healthcare professionalism in making more informed decisions. In addition, uh, basically have the mobile and cloud-based diagnostic platforms that are being developed to support the rural and resource limited areas. These technologies allow medication images to be analyzed remotely, increasing access to diagnostic services where uh, expert laboratory personnel may not be available for those rural areas. And then finally, we have our explainable AI techniques. So our explainable AI techniques that are improving trust and transparency in our clinical decision making. Instead of simply providing predictions, these systems can highlight the color, the regions, and the features responsible for their diagnosis, helping the clinicians or the clinical doctors to better understand and verify the model's decisions. So we have our problem statement. Our problem statement is classified into two categories. We have the domain application and then the computation application. And for the domain application, neural areas, neural areas, basically going to talk about 3 points. One, neural areas, neural areas of Uganda, the current of diagnosing babesiosis is still manual, blood smear examination and a microscope, and the process is very slow and highly subjective. So it depends heavily on the skills and experience of the micropist, and as a result, farmers and the veterinarians are often experience significant delays in treatment, sometimes waiting for hours or even days to get the diagnosis. That's our domain problem one. Then the second one, another challenge is frequent confusion between the Babesia parasite and the very similar looking parasites like the Plasmodium or the Malaria parasite. So when they are viewed under microscope, both of them have a same ring shape that results into misdiagnosis. And lastly, we have the co-infections. Which is also very frequent. Cattle are often infected with Babesia together with the Theiler and the plasma and other tick-borne diseases. This makes the actual diagnosis even harder and often leads to worse clinical outcomes, high mortality rates, and also greater economic loss for the farmers. So we shall go to our computation problem now. We basically have 3 points there, and I'll take you through them. The first point, we need to develop a robust multi-class classifier that can accurately tell a part of the Babesia parasite from very similar looking parasites like the Plasmodium rings, as well as the yellow blood cells such as the RBC, the leukocytes, in the GIMSA blood smear, blood, the GIMSA stained microscopic images. Then the second point I'll be talking about the media class imbalance, which is also under difficulty. Babesia infected cells make up only 10% of our images, while the healthy ones dominate 17%. And this imbalance makes it easy for the model to become biased towards the media class and perform poorly on the critical Babesia class. Then thirdly, with the system will be able to perform a real-time reliable real-time detection of Babesia when the images come from different laboratories with varying stains quality images, and this adds on a layer for complexity to building the generalized model. So we came up with some research questions and objectives, and one of our research questions is how can you transfer learning on public parasite images data like veterinary grade? How can our model distinguish between Babesia and other similar parasites like Plasmodium? And our objectives include we need to prepare and explore the relevant subsets, develop and train deep learning classifiers, evaluate our model performance, and also demonstrate a prototype inference tool for the new images. Then you have our research contributions and outputs that we got. We developed focused multi-class Babesia detector using efficient before on our public datasets. We had a robustic negative set which was consisted of the healthy RBCs, rebel cells, the leukocytes, and then the plasmodia to reduce the false positives. We also achieved a promising accuracy of between 90 and 95 as expected. We designed and deployed our user-friendly diagnostic interface to support the practical use of the practical use in the veterinary clinics, and we have a link displayed there for showing how it works. Then we have our methodology and system architecture. Our architecture initially, we are going to first identify the problem and then analyze it. We shall go and get our data sets and then do the pre-processing, build our model, train it, validate, test, and then we package it and then so that it can be deployed on different servers or websites. For example, like the Hugging Face, where the users can face it and then use it. So we have our data set, description, and expanded data analysis. So our dataset was got from datamendels.com, which is one of the dataset providers currently. we had our we had our classes, and they had different distributions. We basically had four classes: the Babesia, Plasmodia, Red blood cell, and the leukocyte, and each had a different number of, or a large number of images that we are going to be using. The image format was PNG and JPEG. And then we had some EDA insights. We had the several class imbalance. We had the high visual similarity, and then also the evaluation, the image size, and the staining intensity. So these are some of the results that we came up with. We had our class imbalance, our class distribution. We had basically RBC as RBC was having the highest percentage compared to the rest. We had our class imbalance ratio, still Plasmodium has the 10.7, followed by Babesia with 7.7. Then you have our width variation in the images. We had our image height. We looked at the pixels, the one that has the high pixels, the one that has the low pixels, the width, and then the height. Then we have our aspect ratio distribution by class. We looked at each class, and then we saw the pixel ratio for each particular class. Then we also looked at the file size by class. Then we also looked at the class distribution and the metadata features, correlation heat map, and we looked at the height, the aspect ratio, the file size in KB, the resolution, and each of them were, when we looked at the height, we were looking at the width like that, so that we get our EDA analysis clearly. Then we had the validation or the test split. So we split our data into the validation set, and then the test set, and then the evaluation test. Then we have our calibration availability diagram. We had that before the calibration, which was like that, and then after we calibrating our data, that's what we got, which was basically good. And the mean prediction confidence was, initially it was low and inconsistent, but then after our temperature scaling, everything was coming to our side. So we have our explainable AI and analysis. So to build trust in our model, we applied explainable AI and grade CA heat maps. This technique helps us to visualize, understand which part of the blood images our model is focusing, and when they are making prediction. As you see in some of the examples, when the model makes a quick prediction, it successfully highlights the Babesia parasite ring and the structures inside the red blood cells. This shows that our model is learning biologically meaningful features, and not just the background noise or the staining artifacts. So in most cases, the model concentrates its attention on the actual parasite morphology, which gives us confidence that it is making decisions on the right reason. So for for misclassification images, the grad cam review the model sometimes was confused by the similar ring shapes, the heavy staining artifacts, and also the overlapping cells. So this is our model section and the deployment. I basically made almost like 18, like 16, like 80 model architectures, and on the top we had the ResNet 18. This model uses the ResNet blocks with skip connections. These connections helps the model to learn effectively when it is very deep, it's sustainable and performance, as well as our student model. So look at about that in the model compression. Then you have our efficient net, which is in the middle. It is using advanced design called the MB conj blocks and compound scaling to give us higher accuracy and also more efficient than the old models. We have our mobile VNet 2, which is at the bottom left. This is a lightweight architecture designed for mobile and embedded systems. It uses the bottleneck blocks to reduce computation and making it faster and suitable for real-time detection. So you also have other models like the Inception, the DenseNet, which are also treated as Inception, which means that the multiple filter size is in parallel, and the DenseNet connects. And when you talk about DenseNet, we're basically looking at how it connects every layer to other layers, which helps us to understand the different approaches to feature extraction. And finally, we further went to our best performing model, which was efficient before, that's what we deployed. So we went with the efficient before because of its good and accurate users. We have our analysis that we made further on it. For example, we have the training curves. The training curves are on the left side. We have the training loss, which is in the blue line, and it dropped very quickly and stayed low. Then also have our validation loss, which is the red line, which also decreased steadily with a very little fluctuation. Then on the right, we have the training arch race and the validation arch race, which rose rapidly and reachable above 90%. We also have applied early stopping after the 15 apogées to prevent overfitting, and the base model was saved successfully. So we have our some of the analysis that we can make. For example, the model performance on the test set. We have our conversion matrix as well displayed and the test report on the right. The model achieved an excellent accuracy overall, accuracy of almost like 90, it was 99%, and performed perfectly on Babesia, which is our most important part, with 100% precision and then the recall. Very strong results across all classes, for example, the leukocyte, the plasmodia, and then also the red blood cells. Our confusion matrix shows almost no misclassifications, with only a few in the plasmodia class where the model was slightly confused. And therefore, on the overall, and therefore that's why we went with the efficient before. After demonstrating the outstanding learning abilities, fast convergence, and high generalization on our Babesia dataset. So this is how we went further with our model that we chose. Initially, this is how it works. Initially, we have our interface whereby the user inputs the image, our model makes prediction, and then they gives the results. So we have our core components, which is the trained ML model. What is the fish? That is our efficient before. We have the curated and labeled microscopic data sets. So after giving the prediction, the probabilities that are got from each class are being displayed for further analysis. Then we have the innovation value. And we made disease detection in veterinary diagnosis. However, reduced reliance on manual microscopic analysis. That's one of the innovations that we applied. So it's no longer done manually. Then we went further for model compression. Use model compression. Our deployed model was actually big in size, and we chose knowledge distillation as our compression architecture that we are going to use, so that we can train we can reduce the size of the model without compromising its performance and accuracy. So we had our input. As our texture shows it. We shall start with the input image, which is the game stability mirror. The image is then passed between two models simultaneous. One is the student and then the other is the teacher. So our teacher model is the efficient before, which was large and accurate, and our student model was ResNet 18, which was small and light. And the teacher model produces soft probabilities. These are rich, detained, gen prediction that contain the dark knowledge about how confident the teacher is and how it sees the subtitle difference between the classes. So the student model produces its own prediction, and during the training, adjusts the student's weight that it only learns from the correct answers or the hard labels, but also to match the soft probabilities of the teacher model. At the end of the process, we get our compressed model, which is the improved one that is much smaller, faster, but learned a lot from intelligence of the bigger one, which is the teacher, and that was the efficient net. So we successfully distilled the knowledge from our efficient before. We achieved the competence accuracy. We got a stronger performance with the minority classes, the Babesia, and the advantages that we came up with are the faster prediction speed, low memory usage, and more accessible for the field use in resource limited settings. So these are some of the results that we got from our model. After our compressed model, we had a very good performance in all the classes, and we regarded this to be our final model that we're going to deploy after the compression. The basic class almost had 100% of the precision, the leukocyte 100%, the Plasmodium 99, Rebel Cell 99, and our Achilles was almost 0.99 on percentage, that is almost 99% on all the class, on all the class image, the classes that we had. So our conclusion is that we developed an automated BABESIOSIS detection system using efficient before. We achieved unaccurate and faster image based diagnosis from microscope images, implemented the user-friendly interface using radio. We successfully deployed our model or our ML to Hugging Face for real-time access. Some of the limitations that we faced, the model accuracy was depending on data set quality and then also the size. We are limited to GIMSA standard microscopic images only. We don't exceed that. Whenever I put another one, shall get some wrong results, and was not fully validated for clinical real-world deployment, which we are working on. Our performance may vary due to the power quality of the images, and it is also scalable on Hugging Face. These are some of the references we have. We just gave 5, but in our concept paper, we have almost like 15, or I think we're like 20